All right, everybody. So, welcome to our hardware hacking workshop. And this is like a friendly introduction to hardware hacking. We know that the hardware hacking world is really huge. There are different varieties of way and we can abord this topic, but we are going to be like showing you like the hello world version of hardware hacking with some cheap components and also cheap devices that you probably have riding home. So yeah, if you want at the end or at in the afternoon or in every time you want, you can play with it. So yeah, this workshop is meant for that. So we are my name is Marco. I'm a security consultant too at Bishop Fox, and I enjoy all the hardware hacking stuff in my free time. It's really interesting, and I'm being like starting out with it. So yeah, really cool stuff. And so Abdel, if you want to present yourself.
Yeah, thank you, Marco. So I'm Abdel. I'm also a consultant at Vision Fox, but also working as a manager too. So between us and Marco, we spend a lot of time opening routers, IoT gadgets, embedded devices that are supposed not never meant to be open. So we're having a lot of fun. Today we want to show you how approachable this work actually is, and we can start, Marco.
All right. So yeah, in and as Sean say, if you have any question, drop it in the chat. We are going to be answered questions at the end because of the time constraint we have for the workshop. But yeah, we are going to make sure that we answer all your questions that you have during the workshop. So let's get it started with the introduction. So yeah, before we start like breaking things or something like that, we need to understand actually what we are going to do and why we are going to do it. So the first thing is what is hardware hacking, and when you hear the word hacking, it's normally associated with bad actors or people like that. But no, just don't think like that. It's like hardware hacking. It's not only like the sake of exploit vulnerabilities, but it also refers to like the full process of analyze a hardware, in this case, a hardware device, and understand how it works and how you can actually modify it to make it perform better, to install any new software that you want, extend its functionality, because we know that sometimes devices are more capable than marked as. And also, well, another important part is to identify security vulnerabilities in these devices before it reach end users. So yeah, we in this workshop we are going to focus in the identification of vulnerabilities because we are like in the security and cybersecurity world. So yeah, but just keep in mind that some of these vulnerabilities that you're going to come across in the wild are used also for something like sometimes modifying the devices, especially in routers. Some of these misconfigurations are used to actually flash other operating systems and open source router versions. And yeah, so what devices are of interest in the world of hardware hacking? Well, basically, you can think of any device that you have in hand that it's actually a target for hardware hacking in different aspects, in different levels. Also, your phone probably it's not the same as a router or an IoT device that you already have in home, like an Alexa or something like that. But yeah, you're also gonna have some other things, right? Like medical devices that are used in hospitals, and really many of the industrial automation and control systems use PLCs, HMIs, and RTUs, and any other devices that, well, sometimes it's connected to the internet, sometimes it's not, but yeah, it also has an attack surface that can be studied, and also that we can identify some of the crazy vulnerabilities right there. Also, surveillance cameras. Oh, we always know that some of the cheap security cameras sometimes get like compromised, and some of the feeds are on the wild internet, and you can watch it. So don't do it. But yeah, it's out there. So yeah, and many other devices as you may think. So if you think like, for example, some of the game hacking thing, also some video game consoles are targets for this to actually run unauthorized software, or to run Linux, or to run on the other games rather than the ones that are intended for. So
Okay, thank you, Marco. So, why do we actually bother? The number of connected devices keeps growing across every industry and inside thousands of ordinary homes. A lot of them are exposed directly to the internet. Now, some of these devices are part of maybe critical infrastructure, power, water, transportation, that makes them genuinely attractive targets for serious threat actors. And the everyday consumer devices, those usually get compromised to be pulled into a botnet, and then that botnet gets rented for maybe denial of service attacks or spreading malware or just a layer to hide the real location of command and control servers. So whether it's a national grid PLC or a $15 smart plug, there's a reason someone wants in. So our job is to get there first and report it.
All right, and we're going to be going through some of the basic things that we need to understand. There are a ton of concepts, and as deeper as you go into the hardware hacking world, you're going to see that there is not only things to know about security computers and things like that, but also sometimes you're going to go and dealing with electronics and many other interesting topics. But for today, we're going to be stay in the basics and the really basics because yeah, it's what we need sometimes to get started with many of the devices that we have at home. So uh, for the beginning, we're going to start with some communication protocols. And as you already know, any protocol, it's like essentially a set of rules that defines how something is going to be done. In this case, well, the hardware communication protocols define how devices are going to interchange information and transmit to one another. And this could be in many different forms, but there are mainly two ways to categorize these type of communication protocols, which is serial and parallel and synchronous and asynchronous. We're going to start with serial and parallel. Basically, serial is one bit at a time on a single data communication line. So yeah, the device is going to be sending byte by byte all the information that it's intended to send. Sometimes this is slower. It depends on the bit rate that the devices can handle. And the next one is like parallel communication. You're going to have like a bunch of bytes coming at a time, sometimes bytes, sometimes bits. But yeah, it's multiple bits at a time. It coming from multiple communication lines. This is an important part because yeah, this gonna depend also define how the actual physical interface is gonna be designed. But yeah, just keep in mind that serial it's one bit at a time, and parallel it's multiple bits at a time. And the next one, it's like synchronous and asynchronous. This means that, for example, synchronous used a shared clock signal to synchronize the data transmission. What does this mean? It's like there is a specific signal that it's like uh, uh, sharing some timing signal that it's used to like transmission data. So all the device that needs to care about it's like sending the data through the actual uh, data line at the right time, and that should work. But there's the other part like asynchronous, and in asynchronous communication you don't have or you don't rely on a shared clock signal, so you don't have like a physical clock signal, so you need another way to actually deal with this. And the way to deal with this is like using a sequence of start-stop bits that actually marks the end and the beginning of transmission. So, but also it's not only that. That's not the only thing that you need to actually establish a communication channel. You also need to agree on speed. Devices needs to have the same communication speed in both ends. If not, we're going to see some crazy things happen when trying to communicate with these devices. And yeah, for this, we have like probably the most simple to understand protocol of all, which is the UART or Universal Asynchronous Receiver Transceiver protocol, which is one of the most used methods for communication, for interacting, sorry, with embedded devices. And this is because it's a simple protocol and it's like also a simple, there's like simple ways to implement this interface in all devices without like a lot of power consumption or something like that. And yeah, as you can see, the communication protocol utilizes two different data lines, transmit called the TX or transmitter, and RX the receiver. And we also have like the normal ground and also the power lines. But that's normally in all devices and all interfaces. So yeah, just keep in mind that the most important ones we are going to be dealing with, it's like the receiver and the transmitter. And as the name suggests, one of the lines is used for receive information, data, sorry, and the other line is used to actually transmit the information. So when we have like two devices want to talk to each other, we need to actually connect it like the receiver from the transmitter to the transmitter of the receiver and the transmitter of the receiver to the receiver of the transmitter. So yeah, it's like a cross connections. You need, if you connect it like in the same way, you're not going to see anything because yeah, this signal is meant to transmit and the other one is to receive. And yeah, some of the most common usage for this type of protocol, it's like debug console. Sometimes devices expose like a debug port that you can use for interact with the device if in case of failure or during testing phases, or also you can see like system logs. Sometimes the application actually in this debug functionality has debug logs, or also like some stack trace or other type of these system, or also you can gain full system access for these devices.
Okay, so as Marco mentioned, UART is how we talk to a device, uh, and SPI or SPI is how the device's processor talks to its own high-speed parts. So the serial peripheral interface is used for fast communication between the processor and its components. It uses a few lines, the MOSI and MISO, which stands for master out slave in and master in slave out. For data going, it just tells you the direction of the data that is going between the processor and the component. It also uses a clock to keep everything synchronized, and chip select to pick which peripheral you're addressing. So the reason SPI matters so much to us is one specific use case. It's how the CPU usually talks to the flash memory, and the flash is where the firmware lives on many of these devices. So if we can speak SPI to that flash chip, we can read the firmware straight off of it, and that's what we actually are going to do exactly on a moment. And just maybe one quick note about the terminology. Older docs say master and slave, but modern documentation uses controller and peripheral or host and device. No, just industry is moving away from these maybe historical connotations around master and slave. So you can find those variations of documentation right now. Next, we have I square C, sorry. So I square C stands for Inter-Integrated Circuit. This also is a serial protocol designed for several devices to share the same two lines. As you can see, it doesn't have too much wires between the SPI protocol. So here we have the SDA for data, the SCO for the clock, um, and all devices share the same bus. And each device uh, has its own address, so the controller can call out exactly which chip it wants. Now, this is pretty much like the most common network protocol that we use uh, nowadays. Huh? So you'll find I2C connecting maybe sensors, small EEPROM memories, displays, little control chips. And for us, it's interesting because configuration data and the small store secrets sometimes right across this bus. And as you can see, also the design of this protocol was not meant to be secure. So you can simply connect to the wires and start listening. Um, then we have other protocols, um, and and beyond these three protocols that we just talked about, every industry has its own dialect. So, for example, CAN it's mainly used for the automotive industry, and Modbus and Profibus for industrial control systems, VGAN for access control, no, the batch reader on the door, one wire, simple sensors. Um, you don't really need to memorize all of this. The takeaways is that when you open a device and see an interface you don't recognize, it probably belongs to one of these protocols. And knowing then they exist tells you where to start looking. Each industry has its own protocol. Figure out which world your device lives in, and then you will get a real part of the recon of the device. Now I'll hang it over to Marco.
All right. So yeah, we talk about like the communication, some of the communication protocols that are found in most home devices. But other important concept that we need to take in account when actually interacting with these devices using like electrical signals, it's like the logic levels. Sometimes we think like one and zeros because yeah, it's basically all of that at the high level layer. But in the lower level layers, like in the in the electricity and all of that, you will see like 0 and 1. It's not like just on and off, but there's like a different levels of voltage that actually defines what as in what state a signal is, and this level and these things are called the logic levels. And yeah, as the slide said, logic levels is a specific voltage or state in which a signal can exist. And you're gonna have different standards, like the most common one is like the transistor logic or TTL, but yeah, there are other ones like the BCMOS logic levels. And the important thing to take away right here is like you're going to have like different voltages for these logic levels that which tell you where to a signal lives. For example, we have like in this image we have like VOH, which is like the maximum output voltage. We have to define the minimum output voltage that we want to have like a high signal, like a low signal, and also and there's like if you notice like this gap in between the zero point 0.8 volts and 2 volts, it's like an undefined region. So at this point, sometimes noise it's like undistinguishable from low signals to high signals. So yeah, so sometimes these levels are to be avoided, and you need to actually use one of the defined voltage signals. And this gonna also depend on what voltage you are dealing with. Sometimes you will gonna be dealing with 1.8 volts, 3.3 volts, 5 volts, or something similar. So yeah, the voltage level is going to be different, but the important takeaway is like you always need to take a look at what voltage actually you are reading, because if you are reading something between the undistinguishable zone, you are not going to be going so far. But yeah, if you have like a voltage like a high and low really identified in these other regions, you're going to be ready to go and to see if there's anything else. As a quick as a quick story, sometimes when you actually plug, for example, the logic analyzers or something like that, you forget to plug to connect the ground, you're going to see that there is some noise and some other signals that are fluctuating from one place to another, and that's because yeah, they are like in an undefined state. So yeah, it's really really fun but really annoying to do it. So yeah, just keep in mind that logic levels help you to do all of that things. And well, we with all of that basics, as I mentioned, there are many other concepts that you're probably gonna take a look at, especially in the electronic side. But for this is what we need for the actual workshop today, and we're going to start talking about what is the actual process that we can take, for example, with the device that we are going to show you in a moment, but also with many of the devices that we have right in our hands or right in our desk or in our home, which is like this is the attack chain. We're gonna start as any other uh, offensive security work, like with the reconnaissance phase, when we are going to start to see first how the physical device is, start to recognize some of the components. Also, we need to gain some sort of access to the internal components of the device. This could be easy, this could be hard, depending of the manufacturer, how actually they manage to make the device repairable or not. Sometimes we're going to start discovering some exposed interfaces in the device that can enable us to actually have like console access or direct access to the system or to operating systems, depending on the device. But we are also going to try to see, after identifying all of these components, try to perform some firmware extraction. And finally, we're going to start analyzing the firmware, which also going to depend a lot of the device that we're going to grow. But yeah, this is like the general process that we need to take a look. And we depict it like as a linear process, but yeah, sometimes it's not like a linear process. You need to jump from one place to another in order to get like the final result that you want.
Okay, so let's talk gear. The good news here is that you can get started with very little money. Most of the hobbyist grade equipment you can order it online today, so we have many options for that. Um, on the hardware side, the starter kit is short. You can start maybe with a multimeter for identifying which pin is which. Um, that is something that we will going to see right away. USB to TTL adapter. That's your bridge to connect to the UART interface from your laptop. And a spy programmer with a soy clip. Uh, that is what clips onto a flash chip to the to dump its memory, and a soldering iron, because a lot of this time those debug pins are unpopulated and you need to solder some headers. On the software side, we will be using mainly flash ROM for reading the flash, terminal programs like Screen, PycoComm, or Putty to talk over serial, Bingwalk to carve up the firmware, and Jidra for reverse engineering. That's the whole toolbox to start with. And Marco is going to show us more about some other cool hardware.
All right, sorry. All right, so the other the other tool that probably it's one of my favorite tools right now because it's convenience. It's like the Tigard, which I called it like a Swiss Army knife tool. Why? Because this is a simple, a small footprint tool that actually have many of the things that we already that Abdel mentioned. Like for example, we can use it to interact with URT. Read also make some memory dumps with ISP, but also SPI, sorry. But also we can interact with many other standard protocols that are found in different devices like I2C, JTAG, SWG, and many others that actually supports the interaction of this. And the most cool thing about this board is that you sometimes when you deal with some devices that are not intended for like 5 volt or 3 volts, and some of the tools that you have only support these type of voltages, you need actually to use something called level shifters. It's not really common to see it, but when you actually see it, you need to actually convert the logic level in order to don't damage the device, and also to that the signals can be well, as we show you, the logic levels depend on the voltage. So yeah, you need to be accurate. All the signals need to be accurate. So the actual TyGuard, I include these ones, and you can select from all these options that are like 1.8, 3.3, 5.5 volts, and also it has like onboard powers power supplies that can also help you to sometimes obviously not to turn on like an entire device, but sometimes it's useful to actually interact with some of the devices that doesn't have like for example, there are some URT interfaces that probably are not connected to the main voltage of the board, but you can actually power it up using some of these tools. Or yeah, and well, the most important thing is that it doesn't require drivers at all. It has like drivers on the board. So yeah, it's ready to use for the vast majority of tools that are available, like OpenOCD for JTAG, FlashROM for SPI, and many of the URT bridges, serial console programs that you're going to see in a minute. So back to you, Abdul.
Okay, thank you, Marco. So, as Marco mentioned, everything starts with the recon. We before we attack anything, we got to know the device better. Okay. So first is the physical access. Once we got our target in hand, we collect the basics. Brand, model, version, and revision. Um, some basic stuff like how does it open, clips, screws, glue, what voltage and current does it need to power on. And honestly, one of the most useful things you can do is just use the device as a normal user. First, set it up, click around, understand what it's for and what is its features are, because that tells you where the interesting attack surface relies. And read the manual if there is one. Sometimes the vendor documents the very interface you're about to abuse. Um, Identifying the main components. So once you get the physical access, you open the device, the board is exposed, and now we hunt for the key components. Uh, you're going to be looking for the main chip, the CPU or microcontroller. No, where's the brain? The memory flash, or the memory if it's a flash, um, whatever the code and the data lives. Also the debug interfaces. Uh, Here in the image, you can see a row of paths and headers that probably are a debug interface. We're gonna zoom this in a while. Anytime a chip has a part printed on it, write it down. Those parts numbers are gold. They're how we'll find data sheets in the next slide. Well, in a while. So just to mention something, important considerations. One thing that shapes everything. Not all devices are built the same. Uh, a simple gadget might run on a basic microcontroller. More capable one runs a system on chip, um, and maybe if it has enough power, it will run a full Linux version. That single design choice changes the whole board, how complex it is, where components sit, and frankly, how much fun we're going to have. Uh, these two devices, the Emporia and this TP-Link, are uh, good examples of how different two devices can look inside. The Linux class devices are where we usually get the richest results because of how much companies they have. Um, so Looking deeper, moving to the main chip, zooming in, here's the processor. Uh, it where it runs the operating system, it controls the peripherals, and it talks to the memory. The names you'll see again and again are Qualcomm, MediaTek, Broadcom, and for smaller smart home stuff, the ESP32. Recognizing this on site starts to tell you what you're dealing with before you've even look anything up. Always look for data sheets, and this is a habit I want to drill in. Always look for the data sheet. Take that part number and wrote down and search it. The data sheet is the manufacturer's own manual. It tells you the pin out voltages, which pins are the debug interface. We are not guessing in the dark when the vendor has already published the map. Free intel every time. Okay, now let's zoom into the flash memory. The other component we care deeply about is the flash memory, because that's where the treasure is, the firmware, the configuration files, some secrets, maybe operating system. You mostly meet two types: the spine or flash, which allows direct access to any address and is great for executing code like bootloaders. um, I would say is the fastest uh, between the NAND flash. The other one is the NAND flash, which packs in more storage, but has to be read in blocks and has error correction. So common makers you will see are Winbone, Macronics, Gigadevice. When we extract firmware later, this is the chip we will be clipping onto the flash. So let's move to the UR interface.
All right, so we're going to see like many home routers, especially these ones that are not really as expensive as like yeah, that are like less $20 or something like that, are use they normally have like this URT interface, and which is exposed for debugging, and sometimes you can also access directly the systems. And as you can see, there are different instances of how you can find these pins, but normally there are like 4 pins in the board actually. So one thing to keep in mind is that at least in this router, it's like a little cheating, because the manufacturer already put like the levels for the for the actual URT pin headers, but this is not normally the case. So you will gonna find instances in which you are the pins actually don't have the labels, and you need to actually identify. And this is where things like multimeters, data sheets, or logic analyzers come into play. So we're going to be jumping into the how to identify your T interfaces with a multimeter. And as I can, as I said, you can see that, for example, this this URT interface in another router doesn't have like these pins as normally they do. So, or these labels. So yeah, the general process to identify this is, first we need to identify a ground point, a ground connection, a reference. It doesn't matter where this point is, but needs to be a ground point. Well, then we need to measure the resistance of the of each pin of the interface in reference to ground, and then, well, we are going to try to identify which pin is which based on the behavior of this resistance value. As you can see, there is like a small yeah, like a small table right here that shows you some common values for these resistance between the different pins. I think that, yeah, the export of the slides got a little moved, but yeah, as you may notice, like ground and voltage, it's always like the highest resistance. And also you can see like then it's like the transmitter and the receiver. And there's also another way to identify this if you are not seeing like resistive really changing resistive values, and it's like powering on the device, and we're going to see that in a second. So yeah, the other idea is to actually bring it on, like the device, power it on, and start to playing with this. So for this, I want to share a video with you of how to do this. So let me just upload the video. Where is the video? Okay, so okay, let me just hang on a second. All right, so as you can see, we have like our multimeter in like the continuity test, and we are going to try to identify first where the ground is. So for this, we are like just like using some reference to ground point. In this case, this reference to ground is like a normal button, or some of
Are you
the
showing something, Marco? Sorry.
yeah, I don't know if it's showing it.
No, it's not showing.
uh, okay, so yeah, yeah, great. All right, if not, let me just, you know why, let me just share the screen and I can put the video. All right, give me 1 second. All right, so hang on. Here is. Okay, so share screen. And we can see like this video. Okay. So, all right, so as you can see, we have like our multimeter right here and all the pins that we already populated and soldered the pins. So we can put it like in the continuity testing of the multimeter and start for probing for different reference to ground actually. So the first one that we like I came in my mind is like sometimes these metallic parts from buttons and other connectors are actually shielding parts that are actually used for yeah, just like plugging in the for yeah, and these are reference to ground directly, but you can also use like the barrel connector that you can see over here, or any other connection to ground that you have. All right, so let me just get back to the presentation, a little quick presentation. I think, Abdul, can you share again the
Mm-hmm.
presentation, please?
Yes.
Thanks. All right, thanks. Oh,
Okay, you have control now.
all right, thanks. And yeah, okay, so let me just move it again. I think that was weird. I think it was, but yeah. All right, so once we have identified like the ground pin, we can actually start identifying other things like the receiver and the transmitter pins. And for this, as we mentioned, we can use like the measuring the actual resistance between different pins, but we can also try to actually well, use power on the device and see how actually it behaves. Yeah, so let me just share again in the a video. Share something else. I think yeah, this should be fine. Okay, sure. So all right. So we have here again our multimeter. In this case, we are going to put it like in DC voltage, and we're gonna, as you can see, the device is turned on from the little these red LEDs and green LED, and we can start to see like when we prove for the receiver pin, the receiver pin stays always as 0 volts, and the transmitter pin it stays like 3.3 volts or around 3.3 volts. And this is because, as you may know, as you already know, for the when we talk about the URT protocol, the URT is only expected to actually share all the receive the receiver pin. It's only meant to receive. If we don't have anything hooked to it, it doesn't gonna receive anything. And if we have like the other the transmitter, actually it's gonna start transmitting if no matter if we are hooking to anything or not. But yeah, that's the whole idea. So yeah, we can. Okay, so yeah, thanks, Abdel. And let me just move it to the other slides. All right, so all right, it's right here and it's right here. Okay, so once we identified our debug interface, the pins and the layout of how actually the interface is going to be working, we can start like taking a look at really how to actually interact with it. So uh, basically, this is like the first step. As you can see, originally our device doesn't have this pin header, so we can use it. We can solder some because it's more, it's easier to work with all of that. And then we can also have like different tools gonna have different devices, different pin headers and different ways of connected. But for using like the Tiger one, you're going to using this yellow connector and the normally the pins 2, 3, and 4, which are these GND, TX, and RX. But yeah, this is everything that you need to know. And as you may notice, you need to connect it in the crossway. You need to put receiver with transmitter and transmitter with the receiver. And you're going to be ready to go. Then you need to connect it to the actual computer and start to like testing and proving it. So let me share again the video. Sorry for the inconvenience of changing the how it's called, the yeah, between one and other things. But yeah, let me just share uh, how it's gonna work. And okay, so this is the media player. Sure. Okay, so as you can see, wait, that's not the media players. uh, Presentation, sorry. Screen, sorry. Window, media player. All right, yeah, that's the media player right now. And as you can see, we're going to have like, I'm using the tool PycoComm. We need to set something called the baud rate. And after setting up the baud rate, as we can see, but well, we can start like interacting with the actual device. So uh, the recommendation is to actually don't power out the device until you actually have all the pins connected, because sometimes the device is going to start, like as you can see, start popping up a lot of information when booting up, and this is gonna confirm us if we have like access to the system or not. Sometimes the interface doesn't do anything after booted up, but yeah, in this case, this is like all the boot process from a normal Linux service and for the router. And after that, you can see that after some time, it's gonna have like this. Oh, okay, you're gonna have this, uh, well, the operating system, and in this case, the root access to the operating system. So yeah, this is really interesting for some of these routers. You're going to see like, yeah, that you have a root access directly without any other problem. So Abdul, can you, okay, thanks. uh,
Okay.
All right, so, and after that, you will see like there are other tools that you can use and probably you have in hand, like the Flipper Zero. It has the functionality of USB to serial, and also the USB TTL adapter that you found in your local electronics store also do the work as fine as the other ones. And as you notice, they have like the baud rate, which is like the way of communicating with all of these devices. And as we mentioned, for URT, you need to actually use to agree upon before receiving the actual speed of the communication you want to have. In this case, the most common is 115200, and this is one that we already use, right? And yeah, so this was the command that we already show you. But yeah, there are other tools that you can actually use, like Screen or Purity in Windows. If you, it's not only like locked to the Linux operating system, you can use actually whatever other software that actually enables you to serial connections.
Okay, great, Marco. So we're moving to the firmware extraction. Um, so yeah, Marco got us a shell through the debug interface, but sometimes you don't get a shell or you want the complete firmware image regardless. For that, we go straight to the source, the flash chip itself. Okay. So extracting the firmware from a spy flash. Um, the beauty of it, the flash memory can be read directly off the board. Um, the general process is a three-step process. First, uh, you can clip a soy clip onto the flash chip. We're going to see an image of a clip right away. It grabs the ship's legs without any soldering. You can connect a programmer. In this case, we're using the CH341A. It's really cheap, and you connect that to the SOIC and to your PC, and then read the chip with a tool like FlashRAM. The command, it's here. It's a really basic command. FlashRAM, the programmer model, and dash R, which means read, and it puts the entire contents of that chip into the file, in this case called firmware.bin. That one file is everything that the device runs. Okay, sorry, it moved back. Let me get. Okay, so here you can see the side clip that is attached to the spy flash. Um, you connect that to the headers or the pinout that is shown here. This is the CH341A. We usually use the ones that are marked in red, but you can also connect to the yellow headers that are on the sides. Um, and I have a really short video. Um, Let me show it to you guys on screen. After we connect the SOIC, the programmer. Okay, 1 second, just to hit play. Okay, so here's the usage of FlashRAM. As I mentioned, we are running the exact same command. And one thing that FlashRAM does is that it proofs before reading the memory. It proofs to see what kind of chip is it running. So there's something you can see here. You can also see that it found that the chip is this one, the EN25 QH32, and it actually has 4 MB of size. One thing to notice is that if you see the data sheet of this chip, you may see that it has uh, 32 megabits of capacity, which are actually the 4 MB of space. So after that, it simply reads the chip, and in this case, it uh, performed correctly. Let me move to the presentation. Okay, so we're on slide 39. Okay, so what happens if flash RAM uh, didn't succeed? Uh, Sometimes what we see is that the clip won't work, the PCB layout crowds the chip, or other components interfere on the bus. In that case, we use the chip off technique. We literally desolder the flash chip, remove it from the board, and read it also in a dedicated programmer like the Tiger or the CH341A. This is a more invasive method, and you need a steady hand with the soldering iron or the heat gun, but it always works. Um, Sometimes you don't need to chip off the entire flash, maybe just some of the pins that are connected to ground or chip select. You can see that in the left image that only 4 pins on the right were desoldered, and we use some Kapton tape to avoid connecting to the pads. So also I can show you. I don't know. I think we're good on time now, so I can show you a really short video how to do the chip off. There are many techniques for this. Um, you can in this case I use I usually use the iron, but you can use the heat gun. Okay, share, and I think you can see here. So what I'm showing here is that we first we pour some flux on the pins. In this way, it will be better to get to the necessary temperature for the pins to desolder. Once we have the flux, we use the iron or the heat gun and start pressing the pins to get the ideal temperature. We use some tweezers to pull a little bit the chip up, and once it's heated to the temperature, to the ideal temperature, it just simply comes off. No, that's it. So after this, we again we can use some sockets or the side clips and execute again the flash ROM or the necessary program to read the chip. Okay, let me go again. There are, as Marco mentioned, other hardware tools for reading the flash. You can use a Tiger or the X um, Giku, also a really versatile programmer. If you're working a lot with chip offs, this is a good option. Uh, and we're moving to the firmware analysis.
All right, so the firmware analysis part is a really tricky one because it's gonna depend a lot on what actually the device is capable of doing. And as Abdul mentioned, the architecture and the design choice of the manufacturer to doing, like, for example, a router normally come with some management interfaces. So yeah, they have like a web application. So you're probably gonna have access to the source code of this application and start performing your standard web application pen testing methodology. But you can also find devices like ESP32 that are actually having like just plain binary files, or also the router is using some custom uh, native code to actually execute something else. Or also nowadays you will find like many IoT devices have an attack surface on the web, on the mobile application, that there sometimes are accompanying them. So yeah, it's gonna depend a lot of what actually the device is doing, what you are going to see. But for our example, we're going to see like the main things that you need to take in account when analyzing some firmware, especially, for example, the binary files from firmware. The first thing to take a note is like you need to use some sort of tool to identify the actual architecture, the actual what actually is this that you are analyzing, because sometimes uh, manufacturers actually remove the part number in order to be like more secure, or like don't compromise like intellectual property or something like that. The chip actually doesn't have a public data sheet or something like that. But yeah, uh, there is like many ways in we can find this, and when if we have access to the actual firmware, we can actually use something like, for example, uh, commands like read elf or like file to actually get the architecture, for example, of some of the programs. For example, for the router firmware that we found that the Busybox executable actually it's compiled for a MIPS architecture. So yeah, when we are using tools like Guidra, uh, IDA Pro, or Binary Ninja, we just need to put like this architecture in perspective. And also, well, after, if you are curious about how some of these thing works, basically what we are looking is for like inside the ELF, for example, the Linux ELF files, we can see that there is a structure that actually defines in the header what our architecture machine is, and you are going to see like there is a ton of different architectures based on this, and yeah, the tool is only searching for that. But yeah, overall, we are going to see how actually this is gonna work. We can use tools like Beanwalk or something like that. Uh, but yeah, this is like everything we can do. For example, in this firmware, we found like a small credential that it's actually uh, a really insecure credential that that yeah, this is like a really insecure credential that was actually cracked using Hashcat and RockU word list, which is really fun. As you can see, yeah, this is the only one. And for tools like that, you can use Pingwalk to carving the files, strings, or and all the other tools that you have available at that point.
Okay. So another tool, I'm just gonna talk about it really quick. We're not expect that to see too much in deep about Jitra, but another great tool when you not when strings or being walked doesn't give too much information, you can start analyzing the binaries, reverse engineering, and Jitra is a really great tool. I think we're all covered for today. We're a little bit past the hour, but we can move to questions. I don't know if anybody else has some questions. I think we have a question from Rodrigo
Yeah.
Vega. Yeah. Do you want to answer that, Marco, or?
Yeah, I can answer that. And first of all, sorry if this last part it was a little quicker, but yeah, we can cover in an hour a lot of the firmware analysis because it's a whole workshop for that probably, and we're still missing some time. But yeah, the question from Rodrigo is really interesting. The question is it related to logic levels? Is related to how when incrementing the voltage of certain devices, they can do unexpected actions like intentionally doing it to bypass something, or that's more a movie thing. Well, this is actually a thing that it's actually possible to do, and it's called fault. There's like some sort of different techniques around it. It's called fault injection, and you can use it like it's like using different effects like timing, voltage, to create some glitches in how actually the processor and see how the processor reacts. So yeah, it's possible and can be done with voltage, can be done with electromagnetic interference. Sometimes they use some diodes, laser diodes that actually do this type of thing. So yeah, they're not like fictional things, but they are really really complex research that are surrounding there, and there are really really cool examples on the internet. Sometimes using like the flash from an old camera also works.
Yeah, sure. You can also find it as glitching, for example, if you wanna take more a look on that.
Favorite devices, whether
Uh-huh.
favorite for beginners or for favorite overall, other than TP-Link. Well, I think probably whatever router you have available, probably it's gonna have its attack surface, really, really interesting attack surface. But also, if you have like some sort of IoT like this, intelligent devices or an old device that you are not using right now, for example, a Bluetooth sensor or something like that, this is probably also a really cool way to actually interact with some of these sensors. There are some sensors or like electrical readers that actually have are really capable of. And as we stated in the beginning, the purpose of it's not only finding vulnerabilities, but also if you are like a hardware enthusiast or a smart home enthusiast and you want to integrate something with Home Assistant, probably that's also going to be a really interesting path that you can take for that. I don't know if you are also
Hmm.
gonna answer some of or complement what I'm saying.
Yeah, sure. Maybe if you're starting with this world, some of I think the coolest devices will be the ones that are meant for developing. So, for example, you can use the TP-Link, but there are also some other routers that are used for development. And a good thing about that is because they're um, fully documented. You could also find the pinouts really quick. So I would also recommend some of those. Um, Thinking maybe like a Raspberry Pi, but also there is a router that is, I think is called, it's a mini router that we use on one of the worships, the lay worship. I think it's called the GR 600. Maybe I can search for that right really quick and answer that. But yeah, try to find maybe devices that are meant for development. Yeah.
Yeah, and last question that we have right here, how often is possible to connect to the bug interfaces using PycoComm? Is it normal for hardware to expose the bug stuff? Well, this gonna depend a lot on the manufacturer and also on how on the device itself, because there are sometimes like these interfaces have its purpose to actually debug something during the production phase or during the development of this. But well, actually, you are not going to see some of these stuff on real production hardware, or if they are in real production hardware, sometimes they are like the chip can be enabled to actually, well, the chip actually disable this functionality, and you need to actually perform some other crazy stuff, or sometimes it has like resistors soldered to block the actual use of the device. But yeah, it's not it's gonna depend a lot, and you need to take a look at how your device is actually using, and also what type of debugging interface it's using, because and most modern devices sometimes use like, and more complex ones use GTAG instead of URT, and that's a whole other thing to actually take a look at it.
Yeah. So yeah, they posted one. Yeah, you can use that one on the link you share, and that page has a lot of other devices that you could use for testing also.
Yeah,
Um,
and yeah,
there's one.
oh,
I don't know if you have it on hand, Marco, but the one that we use on the workshop last
uh,
last time.
the
Yeah,
routers, I
it's
think I think the only one that I have is this one. It's yeah, it's an old router that I have in in home, and I take it apart completely. But yeah, uh, the important takeaway right here and the purpose of this workshop is to show you that you don't need to have like the most expensive gear, the most expensive tools, or the really complex devices to start like taking a look at what is actually or what you can do with hardware. The important thing is that if you have all devices at home that you don't use it anymore, or your or friends or someone can actually give you some of this, and you can actually start poking around with all of these things, and you can use yeah, devices like the Tigard and things that are more sophisticated things and specialized tools. But you can also use these cheap clip adapters that cost like $5 to $10 or less on AliExpress or something like that, and just start to play with all of this.
Okay, good.
All right. Well, thank you guys so much for to everyone who showed up, and of course to Marco and Abdel. Very fun workshop. I think a lot of people are going to be ripping a lot of electronics apart after seeing this, so that's very cool. We shared a link to our survey in there. We also put a little link to the router that he was talking about and that Abdel mentioned. If you have any other questions, feel free to hop in our Discord server. If you're watching this online on our website, it's discord.gg/bishopfox. And we're always in there talking shop. So yeah, thanks again.